We have already seen that an atom consists of a tiny positively charged nucleus surrounded by a much larger diffuse cloud of negatively charged electrons. Let's see what happens when two atoms come close enough to each other to form a chemical bond. When two neutral atoms are far apart, the electrostatic interactions between them are small, and the energy of the system does not depend on the internuclear distance or the separation between the atoms. However, when the atoms approach each other close enough for the electron clouds to start to overlap, the electrostatic interactions of the protons and the electrons can be favorable, so the potential energy of the system decreases. At some intermediate distance, the potential energy reaches a minimum, and a molecule is formed. But if we were to force the system to even smaller distances, the energy would increase again sharply. This happens because the electron-electron repulsions overcome the electron-proton attractions, and these forces will push the two atoms apart to reduce the overall energy of the system. Perhaps the clearest way to understand the nature of the chemical bond is to recognize that one must supply energy to the molecule in order to pull the two atoms completely apart again. This amount of energy is called the bond dissociation energy. The bond formation process is complex, but we can gain some basic understanding by considering two limiting cases: ionic bonding and covalent bonding. Suppose we form a bond between an electropositive atom like lithium and an electronegative atom like fluorine. At some distance of approach, the system can lower its own energy by transferring an electron from lithium to fluorine. This creates two ions with opposite charges, and they will attract each other, thereby lowering the energy of the system, until the repulsions of the electron clouds become too great. The electron transfer forming an ion pair is the central feature of this model for ionic bonding. But what if we instead try to form a bond between two atoms of the same element? Here there is no difference in electronegativity, so most of the advantage of electron transfer is lost. This model of covalent bonding is based on the sharing of a pair of electrons in an orbital that lies between the two atoms. Sometimes the energetic advantage is described as allowing the bonding electrons to each feel the attractive interaction of both nuclei. However, the real picture is more complicated than this, and it involves quantum mechanical effects that lower both the potential energy and the kinetic energy of the bonding electrons relative to the separated atoms. Although these two limiting pictures of ionic and covalent bonding are useful for understanding chemistry, it turns out that all chemical bonds involve a mixture of the two types. Generally, when the difference in electronegativity between the atoms is large, the bond between them will have a lot of ionic character, and when the two atoms are similar or identical, the bond will be mostly covalent in character. So if all chemical bonds have both ionic and covalent character, how do we know when to call a compound ionic or covalent? One practical answer to this question lies in observing what happens when we dissolve the material in water. Materials with ionic bonds, which we call salts, will generally dissolve as separated positive and negative ions. On the other hand, covalently bonded molecules like iodine will dissolve as intact neutral molecules. Another difference lies in the structure of the solid materials. In salts like sodium chloride, the attractive forces between positive and negative ions are not localized in pairs of ions. Instead, each positive ion is associated with multiple negative ions, and each negative ion is associated with multiple positive ions. You can see this in the crystal structure on the left. The overall lattice energy associated with these attractive interactions is highly delocalized over many different sites. On the other hand, Molecular solids like iodine contain collections of intact molecules that have strong covalent bonds, and the forces holding the molecules together in the crystal lattice are generally much weaker. Finally, it's important to recognize that many compounds incorporate both types of bonding, because ions are frequently composed of covalently bonded molecules. Here are some of the more important molecular ions that we shall encounter in general chemistry, along with the names of some ionic compounds. Notice that the empirical formulas always contain the minimum number of ions of each type to cancel out the overall charge. Ionic and covalent bonding are two extreme models of the way that chemical bonds can form between atoms. Ionic bonding relies on electron transfer to form ion pairs, while covalent bonding relies on the sharing of electrons between the atoms. We have seen that all chemical bonds have both ionic and covalent character, but in varying amounts. And just to make things interesting, some salts consist of ions that are composed of covalently bonded molecules. Chemistry isn't intentionally difficult, but sometimes it does keep us on our toes.